And okay, so let's begin by looking at Erno a bit. So Erno is an interesting part of C in that it's kind of a very different way of error handling than a lot of programs approaches it. So effectively, most programs approach error handling by using some kind of there's a few ways. So how about we just discuss this kind of in a more specific way rather than just looking at some code. So error handling has really one goal, right? You just want to be able to handle like problematic situations in your code. So for example, you want to handle things such as like files not existing, web requests failing, right? And so as you probably all know, like 404 meaning not found, that's like a very common one that a lot of people remember. There's other ones too, like 500 meaning like an internal error on the server, right? There's like billions of them, right? And so there's other things too, for example, malloc failing, right? And so often having like one be or and or is not actually a good idea. And so there's probably like, I don't know, maybe 5 or 6 different commonly used error handling situations. And so error handling solutions. And so this kind of way we want to approach this is try to use as many as we can in the correct situation. So not just trying to like, I guess, use whatever, whenever, right? But for example, you wouldn't want to use Erno for everything because it's kind of a bit extreme. But you also wouldn't want to just use other methods I'll show you in a second for everything, right? Just trying to like find the right case for the right thing. So to begin with, right, we have a very simple error handling solution that may just be something like, let's say, a TUI, right? And this is reading our string, I don't know, which is, let's say, 12, right? And it will return 12, right? But if we give it like AB, what will happen, right? And so you can look at the man page for that and we can kind of see what will happen if we give it an invalid string. I can actually open this up. We can like read through the man page here and we can go, okay, so what it does is it just use string toll, right? And it passes nullin as the endpointer and base 10. Interesting. So it does not need to affect the value of error known error, which means it probably won't. It's thread safe and everything, but more importantly, it's basically just string toll. So if we look at what string toll does, it takes in the AB, it then takes in something called an endpointer, which in this case is going to be null. Then it takes in something called a base, so like base 10 being like decimal, 16 obviously being hexadecimal, and so on. And so in this case, right, what we're having is this endpoint is basically going to be a pointer to a pointer, and it's going to indicate where the number is ending, right? And so what this will do is this will always return a long. In this case, it's casting it to an int, and this long will be our result, right? And we can use the endpointer here to determine its success. So, for example, if we have like this, then we pass this by reference. Again, it's a pointer to a pointer because it wants to modify the address of where this number is ending here, right? And so what's going to happen here is the endpointer value is going to equal a. We dereference it, right? Or it's just going to equal like this. We could view it as, if that makes sense. Like you're grabbing the string AB, you're indexing it to 0, and you're taking the reference of that, which is going to be this. And so what it's saying is that the number is ending at A, right? And so our program can use this to detect, oh, is the actual number correct? And we see this in probably one of the previous tutes. I want to say like, I think we had one called like file or something that did it. No, I don't really remember. But one of the previous ones, I felt it definitely was one that looked into it. Maybe not. Maybe I'm misremembering. But if we look at, for example, file splice, one of the things we do here well, we don't actually do it right now. We'll do it in a second. I thought it was that, but no, we'll do it in a second. Is we'll have to like pass in these arguments here for like start and end. And the way we'll do it is by using like string toll, right? Or we could be lazy and use a TOEIC. And so that we can detect whether or not these things are actually integers, right? Because if they're integers, then what should happen is the endpointer should be pointer /0. If the endpoint is pointer /0, it means the entire thing was a number, right? It ended at the very end of this. Right? And so we would typically call this, this is kind of a bit of an unusual way of handling errors, but it's kind of like you're passing the error by reference, if that makes sense. So like you'd have like some kind of like error code here, maybe like process something, and you'd pass the error code in like this. That way you can determine whether or not it succeeded or not. The other way would be, this is kind of more common. You have something like this, sorry, error. You'd pass in the object, like this. So like it's you're reading a double, let's say maybe. Passing the double by reference, and so it will return the error. And if this error is like equal to 0 or something, then it's okay. Else it's the error code, right? It's kind of like if error equals null, then it's an error, kind of, right? And so you see this in kind of languages like Go and stuff use kind of a similar way. They typically use what's called multiple return values to kind of simulate this, but it's the same kind of idea. And then there's the final one, which is kind of no. There's other ones too, such as the ability to return multiple things at once, or returning one or the other, depending on situations. So you get like a structure here, right? In this structure, you have like a Boolean, is like is error, but then could also store a union, right? A union, I can't say that word well, which contains like either the error type, which is an integer, or maybe like a string or something, right? And as this result type, you can use this error here to determine whether or not it's error or not. And then this holds the data, right? And this uses what we're talking about unions as well, right? So instead of storing both of them, it just stores one, right? But which one it is dependent upon this Boolean, right? So something's called tagged union. Yeah, I guess. And the idea is that you're tagging, this with some kind of like true or false, or some kind of enum, or some kind of way to determine which one is true or false, which one is toggled. And so in this case, when we're dealing with no, what we're finding here is we're finding that we have some kind of error. In this case, for example, no such file or directory. And we can set as like global variable, and I put global variables in like big quotes because it's not really global. It's what we call a thread local. And so what that means is that if you have multiple programs running at the same time under a process, they'll have individual nodes since they won't collide. So it should be okay with multiple threads, which is like when you're running multiple things at the same time. But it's still effectively global to your program. And so what this means is that anytime you modify this, it will modify it for all kind of places in your program. So it kind of means that if you call a series of functions, let's say you call A, and B, and C, if these all modify error or error number, then what will happen is you only get the result for the third one, right? Because this is the only one that's actually going to be like the last modification. So if you want to handle errors, you have to handle it after each one, right? And so a very common trick in Linux, especially for things like fwrite and so on, or write, I should say, is where people write stuff like, or write's a bit different, but for example, like, let's see, open. So like you're opening up a socket or something. I know, we'll just say open with like a file name or something. We'll say we're opening up a file. Sure. Read. And so we're opening up this file with this read-only flag. A very common way would be writing like this, right? This is actually going to return a file descriptor, so often we like store this in a file descriptor. And the file descriptor here, I believe its file descriptors as 0 are still invalid. I'll have to double check that in a second. But it also, if it's like less than 0, it will be invalid. So typically, I believe this is a bad example because I don't want to use one that you haven't seen yet. Like, let me just double check this one quickly. That's not what I want. That's what I want. Yep, that's fine. It's fine. Think about that. Think about that. Yep, that's fine. A non-negative number. Yeah, that's right. Returns -1 on failure. So it can return 0. So it should just be like this. It still kind of sucks because a lot of these functions instead will return non-zeros and stuff. So for example, what ones would you know? There's like, is there any that you've seen yet? Let's see. They're very common. I just don't think you've seen them yet. You know what? That's probably a good way for me to check. Let me open up over here. And I can quickly check a repository which has it's mainly C, so that will be helpful. Okay, this is good. This will just contain a bunch of C system cores, so I can just kind of show off an example. So if I grab my server, socket again, that's a different. Yeah, a lot of them are returning -1. But anyway, it doesn't really matter. But some of them effectively, and this is not a great repository for a lot of things. It doesn't really matter. But effectively, yes, close that. So effectively, it will say any of the functions that you deal with, but a lot of them will return like 0 for success and non-zero for failure, just how your program does it too. Some of them will return less than 0 for failure, greater than 0 for like some result that you want to use. Some of them will do different things. They all have different values depending upon the function. It doesn't really matter. Really, it's like just look at the function if you want to look into it. But the main thing you have to care about is that Ono is kind of like global state that modifies every time. So if I modify this to Ono ent, I then call this string error function. It's going to give me a string representation of this function. So it's probably just going to give me it doesn't say here. Yes, probably just gonna give me this line. No such file directory. That's it. Right? Maybe depending on like some systems and stuff, I'm sure there could be cases where it would tell you what the file is and so on, but in most cases it won't, right? In the cases we're dealing with, it shouldn't. It will just say no such file or directory, because that's the specific error. Now this string error function is actually not really thread safe either. It's kind of really bad to use, but it'll be fine for this course. And the reason why is because basically how string error works is just this big static internal buffer, let's say 1024 bytes, and all string error does is basically, I think it will take the error code in, it just kind of like does a big statement on the error code. It doesn't really like has a table it looks up all the errors from, but that's okay, you can think of it this way. And it would kind of do something like this, because hey, if it's this error, then what we want to do is we want to say memcopy buff. I guess string copy is fine. Buff, and then we can just say like no such file or directory, right? Now, in reality, what you could do is, since these are error codes, you just have like one big array of them, right? Let's say you have 100. Each one could be like this and so on. And technically it returns a const, sure. I believe the reason why it doesn't do this, why it doesn't just like return this string here, and why it has to put it into a buffer, even if you do it this way, is because of something where the fact that even though this is a const that it returns here, it doesn't stop people from modifying this memory. And so I believe the reasoning why it does that is because if you could modify this memory, you could change the error code. And like even though like it's const, you could remove this const very easily. And so I believe it's just like a security thing. It could also be due to the fact that this will be running in kernel memory. So the kernel address space will be different to the client address space. I don't know whether or not this is user code or not. I believe it is user code, so in that case it really wouldn't matter, but it doesn't matter. And so if this was running in kernel mode rather than user mode, then you couldn't access this memory anyway, and you'd have to use a buffer to store it. But it doesn't really matter. This is kind of a bad way of doing it. The better way is string error underscore r, and we'll see that in a second if I scroll down. And this string error underscore r, as you can see right here, takes in a buffer and a size, right? And we'll write it to your buffer.
This is much better because basically it's your buffer. It's not going to affect by other functions, right? Because obviously every time you call this, if it's using the same buffer, right, then what will happen is it will update this internal buffer. I kind of show that here, where I change the error number, and then print out temp again. I believe this should print out the error message for this one, whatever it is, which I think is like invalid attributes or something. Even though I haven't saved the response of this, just because it's using the same buffer. That may depend on your system or not. Especially if you're on Windows, this could be very different because Windows has a little bit of an interesting implementation of some of these things. Anyway, so string error underscore r is slightly better. And then probably the best one for you guys is just use p error. P error is the best because basically it just prints out the error, and you can give this kind of this nice little beforehand. And so all it will do will print out the error in this format. So the string you give it here will be placed here. Or add a colon, I think, and then followed by a space and the error number. So it's very nice. It can kind of like write the error quite nicely. It's pretty straightforward to use, and furthermore, it's just kind of like the easiest one to use. Don't overcomplicate things. Keep it simple. Anyway, so let's move on. We have files, extensions, and hidden files. So this is, I guess, like somewhat. Like, it's just kind of like the part of the course where we kind of diverge into less of like C and more theory. So like, I think the only important part of like files that you really should take away from this course is that files really aren't special. There's nothing ever really special about files whatsoever. It's kind of a very useful thing because I think a lot of people get caught up on the fact there's a .c here and the fact there's like a .md here, or this is a hidden file, .ignore, and so on. They get caught up on all of these like specifics, but in reality, they mean literally nothing. The extension has nothing on what the actual file is. It basically just dictates the uses of the file, not the actual contents of the file or anything about the file. So the .c is just for programmers to be able to basically tell, oh, this is a C file. It doesn't actually differ from any other kind of file, right? So files always store that's the same kind of thing, which is data, right? They always store bytes. What matters is what we call the encoding of that file. So in this case, the encoding of this file is UTF-8. And if I open another encoding, you can see there's a lot of encodings. And these are just a few, right? There's many more. UTF-8 is probably the most common. If you're dealing with the web, if you're dealing with Windows rather, it could be UTF-16, probably little endian. And there are other ones as well, but these are typically probably the only ones you'll see. Sometimes you'll see ASCII, which will probably be somewhere in this list. I don't know if it will be because it's basically just the same thing as UTF-8. It's just like a subset of UTF-8. There's other ones too, such as like, there's Japanese alphabets and so on. These are specific per country, but UTF-8 covers everything. And then you've got special kind of encodings like this. So this encoding here is just plain text, which really doesn't have encoding in this case. As I said, it's UTF-8, but this could be ASCII, it could be many things, right? And then you have literal binary files. So for example, if I go and compile, let's say I go and compile byte slice. CC byte slice like this, right? It's going to, once it finishes compiling, actually produce a dot. You compile. Wow, why did that take so long? It's going to produce a a.out file. Now, this a.out file, as you can see here, is because it uses binary or an unsupported text encoding. Right? So in this case, it's going to be using binary. And so if we open up this binary file, we're opening up in terms of UTF-8. So we're basically viewing this file as UTF-8. Which is why we get all these random symbols here, because these are invalid symbols, right? Because this is not an actual UTF-8 file. It's literally just a binary file. And the reason why we can read some of it is due to the fact that these strings exist in the file, right? And these strings are going to be stored in UTF-8 because they're strings. They're like human readable things that we want to print out. So we want to store them in a format that people can read, which is going to be UTF-8, right? And so we can see there's just an absolute load of stuff here. And I think I compiled byte splice. And one of the interesting things about byte splice is it has this really nice string up here. So if I Google byte splice, I should be able to find it. Right. Yeah,
Yeah, here it is, right? So it's just going to include all of the strings from your program across everything, right? And so you see there's going to be absolute tons of them. Like I could look here and see what's here. I don't really know what this is, but presumably it's something. Maybe it's just be random data that just so happens to have overlap with the characters. Probably in this case, it doesn't look like it's anything special. Yeah, you have other stuff here, for example, string error and so on. This stuff doesn't really matter, but it's kind of cool to look at, and we'll look at it later, like shoots. So a file is just binary data that has some kind of encoding to it. Keep in mind that the actual underlying data is basically the exact same for every single file, right? It's just what meaning we're giving to that data. So like it's all just ones and zeros, but we're saying, okay, if this is A4, it's this. If this is 92, it's this, and so on, right? It's what we're interpreting each byte as that matters. Again, doesn't matter, doesn't change anything. And hidden files just don't have a name, they just have an extension effectively. So if you see this gitignore file or this .NoJekyll file, where my gitignore is, there it is, right? This doesn't have a name, it's just a dot. And basically just says hide it, right? Most programmers will probably turn that off, especially as you start to do more stuff. It's kind of annoying to have it hide it. But I guess we'll see. As you kind of use it, whether or not you want to hide them or not. Anyway, so the rest of these functions we'll go into in a second. We're just basically going to do 2 examples and look through some more code. It's kind of going to be a bit of a code-heavy week. So fopen, as you probably some of you've done maybe before if you've done 2x21, I don't think 1511 teaches it anymore, so that's kind of annoying. But effectively, files are pretty straightforward, luckily. But if you haven't seen them before, they may be a bit confusing in terms of how they work. So if we look at this fopen here, right, effectively it's going to take a path which is just going to be the name of the file, fully qualified, right? Sometimes you can have like double dots and so on in it, but the idea is it's the full path to that file relative to your current directory. So if we're running the file in 2.8, all the file paths will be relative to 2.8, right? And so relative to the current working directory of the process. And so that's, I guess, pretty straightforward. It has to be constant, so the fopen will modify this path. And then you give it a mode, which is like, how do you want to open it, right? So there's many modes. There's like read, write, and so on. And the important thing about it is the string. So if I look at fopen here, for example, I'm saying I'm opening this in read mode. I can also open this in write mode by using R+, right? So this is read and write. I can also open this in just write mode. And if I do W+, this is write and read. And then there's also append, which is going to add to the end of a file. So appending will always push to the end of a file, and obviously append plus is appending and reading, right? There's other ones too. We won't really get into. There's quite a few, especially there's some things like RB and so on for that don't really do much. Like if you look at the fopen page, right, we can look at all the ones here. These are the main ones, right? There's also an optional X causes it to fail if it already exists. You can also use optional E's and so on. You can also include the letter B after either the plus or the first letter. So RB will work, RB plus will work, and so on. It does not do anything. The idea is that on some systems, it was important for the system to determine whether or not the file was opened as a binary file or was opened as a text file. Now, as we all know, it's the exact same thing nowadays, especially in Linux. But I presume maybe at some point it wasn't. But so strictly for compatibility, you can add a B. I prefer to always add B if I'm going to use it as bytes. So if I'm not actually going to read it as like text, like A, B, C, if I just want to read it as like raw data, I'll use RB. This is like a way to signify to me and to people reading it that this is how I'm using the file. It's up to you how you want to do that. So if this thing fails, what does it do? So if it fails, it's going to return null. So it's kind of like a dual failing system, right? So it's a simple fail, and then we can get more information by using error no, right? So in this case, if this is going to fail, fn will be null, which is going to be 0, so we can use a special not sign. It's basically saying this, right? But the way it works is that null is fine to be mapped as 0. You can do that if you want. Technically, null does not have to equal 0, but 0 always equals null. It's like this weird relationship in the C standard. And so how it works here is that if I say not fn, if this is equal to 0, then it's going to become 1. If it's anything else but 0, then it becomes 0. So what this means is this is null, it's going to become 1 and print out the error and exit. So for example, if I just show that quickly, let's do file spice. Right, and then I run it out and I give it an argument. Let's say A and then 1 and 2. What I'll find is I'll take invalid arguments. Oh, because I go get more. Okay, how do I give so many? So I'll give it like C. Such file directory, as you can see here, right? That's what this is. You can see how I'm printing out the file name. So the file name A here is being replaced here, and then it's giving me the error message that I said before, and then it's going to give me the usage and then exit. Okay, so let's look at just file splicer. This is kind of useful for your lab. So we'll go into a bit of detail. But there's also 3 other functions that you'll use quite a bit in the lab: fgets, fputs, and fgetc. They're pretty straightforward in what they do. So fgetc is basically great for dealing with 1 character at a time, right? And so if we open up our man page, we can check all these in more detail. We can see, okay, fgetc takes in a file path, here we can see, and returns an int. So it returns a character for that file path, and it returns EOF if it's EOF. Right? So it's great for reading 1 character at a single time, so it's fine. Then we also have the other ones, for example, fgets, right? So fgets is kind of quite dangerous, or rather gets is quite dangerous. Fgets is fine because it has a restricted size to it. The reason why gets is quite dangerous is because it has no buffer. Right? So you can see here, well, rather it has no like buffer size, so it just takes in like a string. So what that means is I'm giving it a string to like write into. So for example, I would say something like this. It's buff, right? And so what it's going to do is going to read from SDN and chuck it in buff. Now this is a very bad idea because we haven't given it the size of the buffer, which means if I give you more text than 100 bytes, you're going to have problems. You're going to like keep reading and then keep writing to the buffer, which is going to be past the end of the array. So it's going to start writing to like this and so on. It's just going to keep writing all the way down, which can like ruin my variables, cause to be wrong, like changes like trues to falses, and it's called buffer overflows, and they're probably the worst class of bugs in C, other than memory leaks and like memory bugs and so on. Like buffer overflows in terms of like when you don't allocate enough memory, or you allocate too much, or you go outside like a heap allocation. So fgets is better because it has a size to the array. Right? So you can say this array is only big, so only read this many bytes. Right? You always give it the string. And the final one, which is I think fputs, yeah. Fputs is pretty straightforward. You just give it a string and a stream, and it's just going to go for every single character in the string and print it out of the string. That's it. And this is secure because obviously we're doing it the other way, so the string is obviously can't be like infinite. As long as you terminate with a /0, it'll be fine, and it'll just print it out. Okay. So let's go through file splicer. And basically the whole point here is just going to be looking at this file. We're going to be splitting up into a sequence of bytes. And this is a bit different from the chew, I think, because it's like more beneficial for the stuff you're going to be doing, but I don't know, as we'll see. And the idea is that you're going to be kind of iterating through the file, and you're going to be having to like seek to the start position, read to the end position, seek to the start position, and read to the end position, and so on. So that's just splice up a file into a sequence of sections, each being output to each of these files. My brain is working much slower today for some reason. So, for example, here, if we have this file, 1, hello, hey, cats, what's up, dogs? I don't know why I wrote there. And then we're basically going to read in this file 1. I think it's going to be the file name. Yeah, if that makes no sense. So if we read these file names here, and we're basically saying, hey, split up between 1 and 3. In this case, I think it's based on lines. Yeah, lines. So in this case, it's going to read from line 1 to line 3, and byte splice is the byte one I was talking about. And so it's going to basically include hey and cats, right? This is, I think,
non-inclusive, and we can see that by this syntax. This syntax is quite common in comp if you haven't seen it before. It's a mathematical syntax, and basically the square means inclusive, and the kind of curve parentheses means exclusive. So it means including start and not including end. Especially Andrew Taylor, I think, likes using it quite a bit. At least I've seen it quite a bit in Andrew Taylor's materials. So remembering it is probably a decent idea. You can always obviously Google it. It's not too hard to Google. And we're just going to do this infinitely, right? So we're going to do n sequence of pairs. And so you can see here, I've done a modulus here to say, hey, you always have to have at least a pair of 3 basically every single time. If you have like missing one of them, it's for error. So it's just going to keep going. Read 1 to 4 into file 2, and then read 5 to 6 into file 6, right? Okay, so luckily this is not too bad. This is actually pretty straightforward. So all we really have to do is just like loop through every single line. The hard part though is figuring out how we're going to do this, right? So effectively, the first step is to kind of read in our file name here, which we've done. I have the first argument, right? This thing. And then we're going to open up in read mode because we also got to read it. If it fails to read, we're going to error. Now what we want to do is we want to read each of these pairs here, start and end. So we're going to say for int I equals 2, I is less than obviously I plus equal to 3. So the idea is that we're going to grab each pair 3 at a time. So we're going to start at 2, and then add 3 to get to B start, and add 3 to get to C start, and so on. So we're kind of going in groups of 3. And then we're going to basically read each of these in one by one. And just using the same trick that we mentioned at the very beginning, using string toll, right? So we're reading in each of the arguments, each of the lines one by one. If this fails, there's a very quick way we can check. So if n pointer is still null, that's a problem. Or if n pointer does not equal /0. So if either of these situations are true, then we've got a problem, we've got to handle it. If I could spell n pointer. So if this is wrong, then what we can say is we can say, hey, this is not a number. So we can give the argument of I, and we can basically say usage and x at 1. Right? And so now we're just going to repeat this like 3 times, or once more rather, not 3 times, for the end. Right? So the end is here. So we're just going to set the end pointer to null again. We're going to grab the end, and it's going to be I plus 1 now, and I plus 1. Right? So obviously you can try to wrap this in a function. That's probably a good idea to make it a bit smaller, but in this case it's fine. It doesn't really matter. So we're reading the start, we're reading the end, and we should be good. Now the final step, right, is obviously to read the file, the actual file that we want to chuck this out to. So the reason why you can do this, or the way we can do this, is by writing like this. So we're going to grab the argument. It's 2 more. So if this is, for example, 0, this would be 1, and so this is 0. This would be 1, and this would be 2, right? So we're going to read that out. This is going to chuck into another file. Right. Hopefully this makes sense so far. We're using write mode. The interesting thing about write mode is that if the file already exists, it's going to truncate it. So it's basically just going to squish it down so that it's always a new file every single time we open it. Right. We're going to use the same trick. I write this trick a lot just because it makes the code. Honestly, I just like it, I think, aesthetically. But I guess you can try to make it a bit more readable if you're not used to it. It does make things like shorter, I guess, and some shorter code is better. Sometimes it's not. Then we can do a clear error here for our file name, out, and a usage and an exit. So we're just looping through, and now I've got all the files open. Now all we have to do is find the actual line that we want to begin at. Now the first important thing to recognize is that the lines start at 1, not 0. Just aesthetically, for some reason I did it that way. It doesn't really matter. And so really all we want to do is we just kind of want to loop through until we find our current position. So the easiest way to do this is just go, hey, while we're less than start, so while we've still got to read stuff, right, we want to read every line. So we're effectively going to read every line one by one, but we don't know how big every line is. So we're just going to read them character by character, and then every time we see a /n, right, every time we see a /n at the end of every line, we know that's a new line. So
we can kind of process it that way. So in this case, we can just say, hey, grab the current character using fgetC. Right? And then, if it's equal to /n, we've incremented our line. Else, if it's equal to OF, then we can break. Now we note here that we don't say this is a character, it's an int. And the reason why is because it could either be a character, which is greater than or equal to 0, or it could be less than 0 and be an error, like EOF. As you can see here, right? So if we say character here, then that's wrong, because the character is typically unsigned, right? It probably it will still work, because unsigned conversions are, well, maybe not, because if it casts them both to int, it probably won't work. Anyway, it doesn't even matter. So depends how it like casts it, right? Because obviously -1 as an int is just going to be 1 1 1 1 1 1 everything, right? But if it's comparing that to C, then the C -1 from this would necessarily be that. I guess it doesn't really matter. It still should be fine regardless of how you do it, because if you do a character here and it's -1, it will just become the maximum value. So it should be fine. Doesn't really matter. You still have it as an int. Because if you do it the other way around, it's like bad style, because like you're kind of abusing it. And also technically it could be like greater than 127, like the character value, right? It doesn't always have to be like less. This is a byte, right? So it can be anywhere between 0 and 255. It just can also be -1 1, right? So between 0 and 255, also -1, or like maybe -2. I don't think it can be, but it could also be other things as well. I only believe it can be UF. So as you leap through, that's all we need, and then we're basically going to do the exact same thing for end. So in this case, we're just going to leap through each one by one. For your assignment, this is probably what you want to look towards doing. It'll be much easier for your second assignment. When you get it and you look at it, I recommend highly to kind of think about trying to do things as simply as possible. Reading characters one by one is often a very easy way of treating these problems. You really don't want to try to optimize it too much, because it'll make it much harder if you try to read multiple characters at once. And already behind fgetC, there'll be a buffer, so they won't just be like loading in one character at a time and waiting for the next character, then loading that in. There's going to always be some kind of like buffer that will maintain which items loading in, right? Okay, so the next thing we'll look at is basically just saying, again, this code is identical to this code. Probably could be a function, I guess. And we can say, hey, as long as we haven't reached the end, what we want to do is we want to put out the lines, right? So this explanation here probably needs a bit of explanation. Or this blank code needs a bit of explanation. So the idea behind this is there's a few ways we can kind of come to this conclusion here. The first way is that we basically want to print out every line, right? We only want to print out every line when it's not the last one, because obviously the file, right, we want it to look like this, not like this. If we add an extra new line here, it's going to be problematic. And so we can basically deal with that. I guess the better way of expressing it would be this way. So we're saying, hey, as long as we're not at the end, right? So if we're not at the last line, then it's good. But if we're at the last line, as long as we're not printing the new line, you can still print it out, I guess. I don't really know why you'd care about this. I'm pretty sure that does not matter. Because if it's equal to the end, the only way it'd ever be equal to the end would be if it's equal to this. Yeah, no, but it's this last thing I'm caring about. So I think all you care about is this, right? I think that makes sense to me. Yeah, I think you're right, Joshua. I don't know. A lot of stuff I kind of do on the fly, so I just have some rough notes. So my notes, I said, make sure to add the or C does not equal /n. So I'm just gonna like right up here, then we'll come back to it and see if it works, and we just have a few easy tests. I'm pretty sure it'll be fine. Like, it doesn't make sense why it wouldn't fail, but I just want to make sure that, like, yeah, I don't know, it should be fine, right? Because when it is equal to this, it will be equal to this. So yeah, anyway, doesn't matter. I guess it would only ever matter if you wanted to be inclusive on both sides. So if you wanted to do the read like this, you want to say while it's less than equal to n, so you want to include the last line. If you want to include the last line, in that case, this would matter. Because if you want to include the last line, you also don't want to include the last new line. Right? So you want to include every character on that last line. So when this is equal to end, you want to only include it if it's not new line. That's basically what it's saying, right? You can express this as like this. So, or, sorry, it's not equal. Every line has to end with /n in an ASCII UTF-8 or UTF-8 text encoding. That's the only way you can end a new line. Because lines don't actually make any sense in binary data. There's no such thing as lines in binary data, right? I guess honestly, you could just chuck an else here, just print it in here. Oh, no, that's not true, because you do want to put it at the new line for the previous lines as well. If you just put the else here, what will happen is that you won't print out any of the new lines, because once they hit new lines, they'll trigger this. So you do actually care about doing it like this. Anyway, and so the next step is just to basically handle what should happen at the end of every file. So this is written out the byte range of this file. We're going to use two very nice functions. This function here is a function that most students do not know, and it's an amazing function that will save you so much heartache. It's called rewind. It basically just sets the file to the beginning. I don't know if they talk about in lectures from previous trimesters. I don't think they do. It's really great. The other way you could do it is use fseek. Seek set. Yeah, hell yeah, I remember that. I was like, is it O seek set or something? No, it's seek set. So this is the other way you could do it. You could say, hey, I want to set the offset to 0. Rewind. I don't know, I guess it's the exact same thing, but it's just like aesthetically makes more sense, like you're rewinding the file back to the beginning. It's just really nice, and I guess it really doesn't matter. The only thing you have to be careful of with like fseek, rewind, fclose. Well, fclose is not really inclusive. Yeah, so the only thing you have to worry about these functions, if this is a negative offset, is if you're using SDN. So SDN technically doesn't have this defined on it. It will work in some systems. I don't think it works on Linux. In my rough memory from me looking at like a year ago. I do know it potentially works on Windows, but basically if you try to seek SDN backwards, it won't really work. I believe the main reason behind that is SDN is not actually it's emulated as a file, and basically one of the things that you'll learn about Linux as you go on is that in Linux everything is a file, like literally almost everything. But everything can be expressed as a file. So for example, even like networking, so if you have like a web server, right? And this web server is like sending requests back and forth between a client. You have to like connect to each other, and they typically connect through something called sockets if you're dealing with, it's not as true, but they typically do. And these sockets are kind of just like, I guess you can think of them as like if you have a computer and you're connecting your computer to another computer via like some kind of cable, and you're sending it across that cable, like that cable is like connecting to a socket, which is probably where the name came from, right? Obviously, in this case, this is over the internet, so it's not physically connected. It's through like the Ethernet or the Wi-Fi or whatever, right? And so the idea is the socket here is actually just a file, so you could just literally just do things like your fwrite. You can't use fwrite. You can use like things like write on it. And the reason why you can't use fwrite is because it's not a file. It's like a file descriptor. So it's still like an integer file, like in like the raw Linux kind of Unix terms, in terms of it's got a file descriptor to it. It can be like rewind, it can be set, it can be seeked, it can be all that kind of stuff. But it's not like a C file in terms of like it's actually got a file pointer to it. Anyway, so it's a pretty interesting way of doing it because it basically means everything can kind of use the same kind of functions. There's some functions that are better for one things than other things. For example, there's when you're dealing with sockets, there's something called rec, and send, and rec and send are actually practically identical to, so rec is for like reading from a socket, is identical to read and write. The only difference is they have a few extra arguments that are entirely meant for like web-based stuff. Like, hey, do you want to just like wait until there's data? Like, how long do you want to wait? Do you want to like just immediately return if there's no data? Like, there's all these like different conditions and stuff. But read and write don't really face that because data is more immediate, right? Anyway, so rewinding files is fine as long as they are not SD in or SD out. In this case, they're not. They're just like actual files. Okay, so this is all you really need to write. It's done. I can kind of show this one off pretty easily. And then we'll write byte splice, which is basically the exact same idea, but we can use some more tricks. We can use seek and set and stuff like that. So I think this will work if I run this. Sure, we can update so you don't ask me every single time. Come on, okay. So let's run our file splice. We have to like cd t3 1521 shoot 8, and then we can just compile, right? Oh yeah, there we go. What is here? And it's created 3 files. What's in these 3 files? Have a look. There's hey cats with a new line, hey cats what's with a new line, and dogs without a new line. Interesting. So it's added a new line. So maybe this was important. Let's just add it and see. And then we can look into why it is if it was. Oh. But for 1, that should be less than. It shouldn't be important. Yeah, okay, thank goodness it is important. Yeah, so we can see the files are here. It was just because this was a less than equal. So what was happening is it was basically having to read 1 more extra line, and that was causing problems. So again, if this was less than equal, if we wanted this less than equal, then we would need this condition, just like I said before, right? Then we would get like the extra line. Less than equal. Because you want it like while it's less than n, so that way that you just have the final one. Oh. Yes, that's what you want. And you here. Awesome. But we're not going to do that. We're just going to do less than n. So therefore, we have to do less than n. Okay. I guess then you probably still would need the new line. You could say less than equal to n. It doesn't really matter. Anyway, so regardless, at the end of the day, it doesn't really matter. That's just the file here, right? So just looping through, printing out each of the ones, and you can get all the outputs here. Now we're going to do the exact same thing with bytes. There's not much difference here. We are just going to copy most of our logic because it's going to be relatively similar for like the reading and writing. The only difference is going to be how we're getting the bytes, right? So it's going to be much simpler, which is nice, but we'll see. So look at this file here, right? What we have is we have a file name that we're opening. Read only is what we're using here. So read only is like the kind of equivalent to R and fopen. Now we could still use fopen here. The reason I'm not using fopen is just to show off the equivalent in Linux, like the lower level forms for this one here, just because I think it's somewhat similar to use. And what we find is that when we use this equivalent, right, we can't really use fget, c, and so on. Instead, we have to use the Linux lower forms. So we'll have to use get c. No, we can't use fget c. We have to use, we have to use like read kind of stuff. Okay, so we'll just have to use, we'll just use the normal ones. Yeah, just come back to that in future weeks when we actually care about it. Because you have to use different functions to do it, and I think it will make it harder for people to compare the two. Because what we really care about is just like the seeking and the stuff like that, rather than everything else. Anyway,
And files are quite interesting. If you ever care, you can right-click this and go to definition on most systems, and you'll be able to see what your file looks like in your system. It's quite large, actually. You can kind of read through this, and you can say, okay, this is like read and write space left for get C and put C, because this is like a buffer. It has like an internal buffer for the file. Interesting. And then we also have things such as like offsets for LSEG. See warning. It's a warning. That's funny. I love seeing warning in other people's code. It's a very complicated warning. Anyway, so there's other stuff too, like cookies. I don't really know why you pass a cookie to an IO function, what that really means. But anyway, look for it if you really care. These are all function pointers, right? Which basically means in like pass a function to a struct to hold it, so you can execute what function you want depending upon the case. Anyway, so we open up this file, read only. It's fine. Normally I'll chuck an RB on it. Doesn't really matter. Same thing here. WB, right? Because we're writing bytes. The whole strategy with this one, though, is that since there's bytes rather than files, we no longer have to care about the line number. We care about the byte position, which makes it very easy for us. Because, of course, we could do something like this, right, where we read each byte one by one. Obviously, we wouldn't have to care about this count anymore. It would just be read every single byte. I don't care what the byte is. I guess we kind of have to care if it's EOF, so we should still read it in. Right, then we should just go like current plus plus, right? This is one way you could do it. It's like read each of the bytes in one by one like this, up to this byte. Once you get up to that byte, keep reading. If it's equal to EOF, we still have to break. Otherwise, we'll just read forever because it'll just keep returning EOF. We can go like current plus plus. In this case, we don't want to read including end, I think is what the spec said up here. Yeah, not including end. So in this case, we want to go, hey, while it's less than end, read a byte. And then I guess we could probably just read a byte then print a byte. Like, it really doesn't matter. Yeah, it doesn't matter. I just keep that there. That's fine. It doesn't make sense to do it here. It's kind of like awkward because like we're at 0. So rather what we could do is we could say if it's like less than and -1 or something or whatever. It doesn't matter. Like, because we want to keep like looping and reading the next byte. So I guess really what we could do is we could just say, oh, it's less than n. If current 0 and we want to read from 0 to 0, then we want to stop. So succeed. If we want to read from 0 to 1, that should be fine. Yeah, so we don't really need this anymore. Okay, so this is one way to do it. This doesn't matter. There's a better way of doing it to express this problem. The better way of doing it is to basically just use a very nice way of reading and writing these, and that's basically to ditch all of this code here. We'll keep it uncommented to the bottom. And what we're going to use is seek. So the first thing that we can use here is a single lseek. So fseek. lseek is the lower form of it. It's the Linux form. So if we're using like the file pointer up here that we're using up here, the file descriptor, we use lseek. I'm going to say, hey, we want to seek this file. We want to seek to start, and we want to set it. So what it's going to do is it's going to go to this byte offset and set its position to this byte offset. Now this could fail, as you can see there's error here, so we can handle it if you want. You can look at what happens with it if it fails. Yeah. Rewind function, which is just this. I don't know. I feel like it's nice. The other thing about rewind that's also nice is the error indicator is also cleared, which is actually, I did not think about that, but that's also nice because it basically means that if you had a file with big problems and you rewind it, then all those problems that you had, like EOF and stuff, could also go away. Otherwise, you still get like a bunch of them triggering. Okay, so there's also set position and get position to like save a position and then get it later on, but to set it later on. Okay. You can see here, these are the errors you can have. Things like overflow and stuff like that. Anyway, so And you can also fail for all these reasons here. Regardless, we don't really care. We could chuck error handling around if we really want, but we don't really mind. So here's the interesting thing that we need to look at. So if we want to read 5,000 bytes, what we're going to do is we're going to, hey, okay, for every single time, right, we can only read so many at a single time, right? Because we're going to use the read function, which requires us to give, I guess in our case, it would be fread. It requires us to give a size and the number of items in a string. So what this means is that we can only read, like, let's say 1,000 items at a time. In this case, we can use 1,024. So the first time we read it, we'll get this. I've written these numbers down, so let's hope they're right. And then the next time we read, we're going to do it again. Get this, and then again to get this, and then again to get this, and then finally this, right? Basically, at every point, it's going to read more and more and more in these many chunks, right? So we're going to chunk the file down to 0. And so we can say the amount to read is going to be basically just the difference between the byte offsets. We can create a buffer. How much have we actually read so far? And then we're just going to do something that's very, very similar to how sockets work, what sockets actually do, which is we're going to say the amount actually read in it's like, I'm going to write it like this because the way it's going to work is going to be different than I think originally intention. So the idea behind this is that we're going to read as many bytes. We're going to read buffer. The size of each item is 1, and we're going to have 1,024 items. And what we care about here is we don't care about how many bytes we want to read. So for example, it's just going to be the amount to read, basically. How many we've got to read. And then we're going to keep doing this while it's greater than 0. So basically, while the amounts that we read from this, because this is how much we read, it's going to be tracked into this byte object. And so while we actually read some bytes. And so instead of having this as a counter that goes up every single time, which I think I was originally going to do, like plus equals, right? We're just going to like set it every time. Because that means that when we actually want to write out the bytes, we're going to have to figure out how much we read the last time. We could just do something like this. Say, hey, we want to write these many bytes out. And wait, it should be the other way around. The size is 1. The number of items is 1,024. Oh, like up here. And then we're just going to read out to f out. And so the idea of this is that we can use bytes here rather than 1,024 to say, okay, only write this many bytes out because we only read 4 bytes, so we only read 904 bytes. Don't read all 1,024, if that makes sense. So we can like restrict how many we're writing. And then we can just say amount to read is minus or equal to bytes. So effectively, this is going to go down to 0 eventually, while we still have stuff to read. So I guess we can say like, while amount to read is greater than 0 and this. Right, well, we still have stuff to read, and you actually read some bytes. Otherwise, this is just going to keep reading to the end of the file, and then I'm not that useful anymore. Okay. So I guess it won't, because what will happen, I mean, this isn't really strictly necessary. I'm going to keep it anyway, because I think it makes the code read a bit nicer. The reason why it isn't strictly necessary is because we're only ever reading this many bytes at a time, which is capped by the size of our buffer. So this is like the maximum cap, and this is like the secondary cap. What this means is that once this reaches 0, it's just going to read 0, right? Because this is how much we want to read from the file. Or rather, sorry, I did that wrong. That's just meant to be the string. This is meant to be fn. What am I doing? And this is meant to be amount to read. Yeah, okay. Yeah, okay. We can't have to do it in an ugly way. That's okay. So we're just going to do it like this. So the reasoning behind this is it's kind of ugly to make it read nicely, isn't it? So we'll write it like this, I guess. Sure. So the rough idea behind this, and why don't we write it like this? This makes it slightly nicer. So the idea behind this is that we're going to read, and we're going to keep reading while we have bytes to read, and we're going to read bytes from the file. And then what we're going to do is we're going to say, hey, if we have less than 1,024 bytes, then just read that many. But if we have more than 1,024 bytes to read, such as this,
don't try to read 5,000 because our buffer is only this big, right? So basically what we're saying is our buffer is only 1024 bytes big. So don't try to read more than 1024. But also only read the minimum of amount to read 1024. That's basically all we're doing is this, right? Minimum of the two. So we could also write this as like, if we have a magical minimum function, just create one, I guess. Let's make the code a bit nicer. Cool. It's still kind of like long. I guess maybe if we make this go to the next line, it may be nicer. Again, this amount to read greater than 0 is kind of not really necessary, but why not? We'll keep it here because I think it's kind of clarifies some meaning. If A is less than B, we're going to return A, unless we're going to return B. So that's it. Is there anything else here that we care about? Nope. And the only other thing that we can do is go remove the rewind because that's not necessary anymore, right? Because obviously we're going to be seeking the set every single time, so we don't have to rewind to the start. And so hopefully that makes sense. We're just looping through, having the minimum of these two. This is quite a common operation. You'll see a reasonable amount. Maybe I can bring up like another example to show you. But that's all we really care about this. And there's one final example here, which is quite small. I won't run this code just because it's the exact same kind of like output, I guess, the previous one, if you get the byte size correct, right? Will be available on the website for you to see. So it should be pretty simple to go through. But there's one final bit here, which is just this reading one. It's pretty much what we were looking at before, which is just the O read only, which is like, hey, I'm only going to read this file. I'm only going to read from this file. Then it's asserting the file pointer is correct, the file descriptor is correct, and then what we're doing here is we're doing the same kind of trick that we're doing here. The reading, we're actually assigning this. This is not equal to single equals, right? So we're assigning the result of this 2 bytes, and then we're checking it's greater than 0, right? So it's a pretty common trick. It's quite nice. So the other thing we care about here is going through and counting all the spaces, I think. Anyway, so we can look here and we can see, check out how big everything is. We can do that. It's fine though. It's just the same kind of idea here, right? We're making it small and small and small every single time. There's only so much space. Okay, so let's just do that final thing I mentioned. So let me just try to find it. So this is a language I wrote ages ago, but had a really nice tokenizer in it. And this tokenizer had a, is it called token stream? I really call it token stream? I did, okay. So token stream has some really nice, interesting things in it. The main one is that it basically uses all the functions that we're seeing here. Right? This is C++ function, kind of a C style, with a lot of C++ stuff as well. Right? It was just kind of like, it uses a lot of C++ stuff, I guess. It just uses like lower level reading operations for efficiency. Anyway, so the main idea of this is if we just look at the main function, I don't remember most of this code. This is probably like 2 years ago now. Where's my read? It must be somewhere. This read function, okay. Here you go. Oh, I've got a reader that has a read function. My gosh, the abstractions here. So let's try to find it. I'm just trying to show you an example, right? Because it's quite common. Here you go. There's a reader class. I guess that's probably it. Yeah, so we can see this is my C reader. I also have a string reader. Read from the string. And so my C reader here just calls fread based on item size. length and a file descriptor. So this last one just /0. That's quite a good thing to do if you're reading, because fread, obviously, if you're reading into a string, right, and you want to process that as a string, it's not going to have the /0 at the end. That's probably something that I really should note. So if you want to use it as a string, like print it out or do anything with it, you have to add the /0 yourself, right? Because it won't do it automatically, because the file won't have that /0, right? Because the file is like just text, right? There's no strings in it. Okay, so you can see here, there's a bunch of craziness. This is all for like parsing a language, so it has to like do. It's kind of cool, especially when it gets to things like when it gets to there's like this entire section around parsing complex something. I don't remember what it's called. Right, I'll look at it. Parse. No, is it called simple token? I think it is. Doesn't really matter. Anyway, so you can look at it if you really care. This will be on just on my repo. I want to read through the code. Anyway, it's not really that interesting. But the idea was that you had this like token set, and you could match each of these tokens, and then what it would generate a big token data, I think, and it would say, hey, for each of these codes, this would all be automatically generated, right? And you also had this like, I think it was like this like map that you should convert. I don't remember where it was, but there's some kind of like map. Was it token list or something? I don't know. It wasn't typecast, that wasn't it. There's like some kind of way that you could kind of. Oh, here we go. Yeah, so in this case, it just like reads the string manually. There's an earlier version of this that would create a big binary tree. If you've done 2x2 so basically it was like a tree, and for each of these characters, it would like check each of them. So basically say, hey, if it goes comma, then only look up the next character. So for example, comma is the only one for comma. A bunch of things have like equal signs, and then some other ones have like equal with a greater than sign. So what would happen is it would check, okay, equals. Now, what tokens have only equals after that, right? So it would go, oh, okay, this can only be either equals or it can only ever be for arrow, right? So it would kind of like break it down to subsets. So rather than just checking like 100 strings, it would check only like 5 every single time, because it could just pull out what's common between them. It was a very fast way of doing it, but it doesn't really matter. This stuff is so fast anyway. It's like checking 2 characters, which is why I removed it. But it was actually quite interesting because it was reasonably fast, and also it was there was something else to it. It was like pretty memory, I think, but basically just created a binary tree. Anywho, that's it for today in terms of the content. So let's just have a look at I'll set up the rooms and have a look and talk through the notes this week. Exercises. So printing out bytes of file, that. This is like fine, right? Like creating a binary file, printing out the bytes of binary file, like it's just what we'd be doing, right? So if you're creating a file of integers, all you're going to be doing is looping through these arguments here. This is maybe something that you're not used to. So looping through these arguments would just be like this while loop here. Like for each argument and argc, just print it out. Feel free to be part of the lab. So the print bytes here, you're just going to print each of the bytes. Again, it's pretty straightforward to print these bytes. You're just going to be looping through the contents here in this file and just printing out each byte one by one. Right? To print out things like this, you'll just use %c, right? Print out something like this, you can use like for example %x, as you can see here, right? This will be the start case of this. The only thing you have to do to change this is you have to add the thing at the very end here, right? Printable ASCII can be determined based upon isPrint function. This function here. It's called the isPrint function. I presume that range is somewhat correct. There may be some cases in that range that isn't correct. It doesn't say. I mean, we could look at the source code for it and tell. Yeah, probably look at that in a second as it loads. And creating a binary file is the exact same thing. These are bytes. So rather than text up here like 40, you put the number 40, like you use fprintf basically.
down here, instead of using fprintf, you're just going to literally grab 72 and like write 72 into the file. Like not the number 72, the byte 72. Anyway, and then finally you got something called borts, which is basically a bort is kind of like it's kind of like UTF-16. It's basically kind of similar to what we'll be doing today, with like the beginning of a range and end of a range of figures. It's basically an unsigned 2-byte big endian number, right? And so you have this kind of range here, and it's just going to be like raw text, as you can see here. And so effectively, it's not too bad, right? It's just like printing out every bort between these files. So really all you have to do to print out the borts is just like iterate for each number and then just printing out the raw data of that. Right? You may have to switch the endianness. I think you probably will, but that shouldn't be too bad. Just like switch the byte order. Okay. Oh, it's macro. See what the macro is. That's very interesting. If you really care about this, the way it's actually defined as is it basically just checks whether or not it's a punctuation character, an uppercase character, a lowercase character, a digit, or an SP, which is a hard space. I can't believe I didn't see that. So it's basically, is print is literally just upper, lower, digit, punctuation, or a space character. So does that mean it's not a new line? Maybe. Looks like it. It could still be a new line. Let's next go for the new line. There's a bit of a divergence, but it's okay. Let's see. So if we look at decimal, new line is going to be, I guess we can look up here. This is space. Definitely copy end line. And null rather. Huh. Interesting, because new line's 10. So I guess it can be a new line purely because of this punctuation. And this is like a trick. Basically, all the oh, that's interesting. No, we'll ignore that note. Who cares about that note? That's fine. We don't have to care about that big warning. I don't know if I would say it's between 32 and 127 because it also includes spaces and stuff. So I think from this, you can like look at this and give it a mask to figure out what it exactly includes. It will include like the, for example, include a lot of this, like include spaces. I think it'll include new lines as well. Include like all this punctuation here. And so on. I think it's going to include anything that you can visually see. This should be what it means. Anyway, that's it. So there's bort, which bort's kind of not too bad either, and then there's extract ASCII, which is probably luckily the easiest part. Basically, all you're going to be doing, it's probably not the easiest part, but it's like the easiest from like kind of already been doing it up here. So all you're basically doing is grabbing all the bytes that are ASCII, which are printable. So all you're going to do is basically read that file and print all sequence of characters 4 or longer where they have printable characters. Right? And that should be also fine. And this one is kind of annoying, but it's quite good to do with fseek and stuff like that because you get used to how the thing works. The idea is that you can't read the entire file. So what you should probably do is you should begin by fseeking to the end of the file. So if we look at, we got seek set.
go seek end, right? So you could seek to 0 or like -1 end. To seek to the end of the file. And the idea is from there you could try to like work your way backwards, one character at a time. Like read that character, seek back 2 characters. Read that character, seek back 2 characters. So, if you want to look at that. Okay. It's good to look at. It's good to process. Anyway, it's fine. Anyway, with big files, make sure you chuck in temp. That's okay. Awesome. Thanks everything. Let me know if you have any troubles with it. Obviously, we'll create a bunch of rooms. I think what we'll do is we'll just create a room for all the individual exercises and a room for the us as well. Awesome. And we can jump into our rooms.